Hi, I'm Dan the Math Guy. We're out investigating how mathematics gets used in the real world. And today, I'm here with Jerry Hauser. Jerry runs the Aeronautical Sciences program here at Palomar College, which means he's training students to become pilots. And Jerry, you were telling me there's quite a bit of mathematics involved in becoming a pilot. I was wondering if you could give us a little overview on maybe what kinds of math you might see in training to become a pilot.
Sure. One of the things that we do is we do performance problems or performance projections to make certain that the aircraft has enough runway for takeoff and landing under the given conditions of temperature and altitude.
Important, yeah.
We do weight and balance problems. We make certain that the aircraft prior to taking off is within the allowable weight limit, also within the allowable balance limits, that the aircraft exhibits good flying characteristics.
So this is how the plane balances that are front to back?
Yes.
So you're finding center of gravity has to be in a correct location for the plane?
That's correct, yes.
Okay.
Mm-hmm. And we do navigation problems. We take into account the winds, the forecast winds at a particular altitude where we're going to be flying. We make calculations to determine where we need to point the airplane, and we estimate how fast the airplane's going to be moving over the ground.
Shouldn't you just point the airplane where you're flying?
Doesn't always go there. The wind tends to blow us off course sometimes.
Oh, I see. So if the wind's pushing from the side and you aim for your destination, you're going to get your drift off somewhere else, so you need to actually counteract that and point your plane somewhere else.
That's correct.
So you can figure out what angle to point your plane at.
Yes.
To get to where you want to go.
Yes.
I see. Okay, that sounds like a little trigonometry. Maybe I could work that out later in some gory detail, but you guys probably have some shortcuts to do it, I bet.
We have the E6B type of computer that we do a lot of these problems on to make it a little easier for pilots.
And this is the device I see behind
Yes.
you.
Mm-hmm.
Is there maybe something simple you could demonstrate for us that we could figure out in there, show us how a pilot might do it?
Sure, sure. Let's assume that we had done a navigation problem and that we are estimating our ground speed to be 120 knots for a particular trip. So I'm going to find the 12 on the outer scale. I'm going to mentally add a 0 to that. That's going to be 120. I'll rotate the inner scale around until the 60 or per hour index is pointed at 120. So we have this set up for 120 nautical miles per hour. In my pre-flight planning, I determined the length of my trip was 85 nautical miles, so I look on the outside scale for 85. I look back to the inside scale, find out that that trip is going to take me about 43 minutes, just a little under 43 minutes. I
see. This sounds like something I could do with a little algebra, but sure. I bet your pilots like this a little better.
It's kind of fun.
But it might be fun to follow this up and see what kinds of so I could work out with math and equations that you're using this little shortcut calculator for. Mm-hmm. Well, Jerry, thank you very much for your time. We appreciate you showing us how math is used in the real world. And we'll look forward to talking to you again.
Thank you. It's fun to be here.
Thank you.
Mm-hmm.
You know, Jerry mentioned actually quite a few mathematical things in that conversation. I mean, so what I was thinking is I'm going to show you a quick one here, but there's many things we could follow up on afterwards. And if there's time today, I mean, maybe I can squeeze in another one. But he was using this little device. I brought one with me. It's he called it a calculator. I know we think of calculators as the electronic calculators, but it almost looks like an old slide rule. Wait, you guys probably don't know what a slide rule is, do you? Well, we'll save that for another time. But it's a little shortcut device to help them figure out things. And in fact, the one problem I saw him use this for, he was trying to figure out how long they would be in flight for their destination. And it really is a very simple little algebra problem. And we can do it quite quickly here, but he did it even quicker than I could on paper by using this little device. So if you want to try and fly planes, truthfully, I think a lot of pilots use GPSs now, global positioning satellites, and they have little devices in their planes or handheld that they can compute all these things quite quickly. But if you do want to learn how to fly planes, you are going to have to learn how to do things old school, if you will, because I think the FAA doesn't want you to depend completely on some electronic device that could go haywire up in the air. So they want you to know what you're doing. So anyway, he's instructing students at our school how to use devices like this. And what he mentioned, I was watching with you guys, was he said, if you're flying at 120 knots, knots is nautical miles per hour. Nautical miles are these alternate measurement systems, and it's roughly, I think a nautical mile is about 1.15 normal mile that you're used to. So it's just a different measurement system, but they often use those for boating and flying planes. So he said 120 knots. I was going to actually show you a little real quickly on, I wouldn't even say it's algebra, a little bit of arithmetic here, what he was doing. He said 120 knots is his plane's ground speed, and that means how fast you're flying, not worrying about what the wind is doing, but if you're standing on the ground watching the plane, this is actually how fast it's going. And the trip was 85 nautical miles long. So the question was, how long would it take? What's the time required? And if you've been in an algebra class, things like this might sound a little familiar because there's all kinds of problems like, the trains are pulling out of the stations and the cars are driving and you have to figure things out. And it's all related to this relationship that rate times time equals distance. So we can use what he figured out pretty quickly with this same relationship. In fact, if I write down what we have here, the rate is 120 knots. The time, well, I don't know, so let's just call it something like t. And the distance is 85 nautical miles. If you take this little equation I wrote and just solve it for t, we are going to arrive, I think approximately anyway, at the same result he did. So I have 120t equal 85. All I'd have to do is divide both sides by 120, and I get the time is 85 over 120. And you know what, if you figure this out on a calculator, this is a fractional amount. If you figure this out, it comes out to be, I believe, 42.5, and this is, oh, sorry, 0.425. This is hours. And if you watch what he did, I'm trying to think. Does that sound about right? No. Hold on. I'm gonna check this. I don't believe my own mental calculation here. So I'm gonna do it on a calculator. I know I'm going lazy here. I had that number in my head. It's 0.708. So this is how many hours we have. And if you think about what he just told us, he had minutes. Well, if you turn this into minutes, just by multiplying by 60, you do get the 42.5 I had in my head. And this is, Jerry, our instructor, said it was a little less than 43. So look how close he was, and he did it pretty quickly on his little calculating device. So he was just doing some algebra. He mentioned a couple other things that are a little more involved. And as I mentioned, if we have time, I'll come back and show you how those work. We talked to our aeronautics instructor, and he mentioned a whole bunch of possible mathematical issues. There is one that's kind of cool I was going to show you. And he actually mentioned that we were talking about, how you have to adjust for angle, because if you fly a plane, usually there's wind. It'd be very rare you were flying a plane, in perfectly still air. So you have to adjust your course for where you actually want to end up and take the winds into account. So I wasn't going to go through all the mathematical details, but I thought I could show you just the concept of how that works. And as I mentioned, he had this little calculating shortcut device, and there is a way to do it with this. In fact, I'll show you on my math cam here. This little guy, on the back side, on our little interview, he showed you the front side. On the back side is this grid of all these angles here, and by making some marks and rotating this dial, you can actually make a pretty good quick estimate of where you should point your plane to make up for the wind. So what's happening, if you want to look at a picture on paper, is let's say hypothetically that you would like to fly from point A to point B. And let's say point A is down here south, and you're simply going to go perfectly up north to point B. The problem is, if you aim straight for point B, and I brought in my airplane today, and in fact, if you'll notice, I don't know if you can see this is actually a Simpsons airplane, which really existed. By the way, this is a model of a real Simpsons jet that was flying around for a while. So anyway, here's my plane. If you fly straight and try and hit point B, but unfortunately there's a wind going, well, let's say the wind is going approximately this direction. What's going to happen is the wind's going to push you a little faster, but it's also going to push you off course. So you're flying this way, and then somehow you end up over here. So how do you know what angle to point at so you actually end up in the right place? And so the idea is you want to counteract the wind. So you'd want to be down here and aim a little bit to the left so that when the wind pushes you, you actually end up where you want to go. And it turns out mathematically you can solve this and find the exact angle you want to do. And as I mentioned, we're not going to do this with numbers. I just wanted to show you the concept of how it would work. So what you could do is we're going to use what's called vectors. And if you get up to physics classes or higher math, they use these vectors. We don't have to be too fancy with these. All I want you to think of is I'm going to use arrows to draw pictures of speeds. So for example, I'm going to take the wind here, and if I were going to use a ruler, I could look how long that wind is and say, okay, that's about, let's say, 30 millimeters. So I would say that represents a 30-mile-an-hour wind. And what I could do is draw that attached right to where I want my plane to land and say that's a 30-mile-an-hour wind. I would actually make the length of this 30 in whatever measurement system I'm using. My plane, I would actually want to point toward where that wind vector starts. So I would actually take my plane speed here. And for example, this would be a scenario, if you look at the length of this vector here, it's about 75 millimeters. So this would be a correct scenario if your plane was only going 75 miles an hour. Now usually, of course, a plane would go faster, but for demonstration purposes, let's say you're in a slow plane, it goes 75 miles an hour, it's cutting through the wind, and the wind's going to correct it or push it this direction by 30 miles an hour. In fact, if you arrange these in a triangle and draw the third side of the triangle, this is exactly what happens, and your true course will be right in the path you want. So all you would have to do is figure out this angle right here of where to go, and you will know which way to point your plane. And with a little trigonometry, we had some trig earlier in the hour, you can actually figure out exactly the angle you need. We have a nice triangle here, and it's not too much trouble to actually figure out the angle there. So our instructor had a nice little shortcut way of doing it, but this is the sort of more formal mathematical method. And the weird thing is, it looks kind of funny, but if you take your plane, it would say point in this direction and you will end up here. So while the plane is flying the whole time, it really would be pointing in this direction, and yet it would travel straight up. So it looks funny, and I've actually seen it from the air. I've been in an airplane, looked down at another airplane flying, and the airplane was not pointed in the direction it was going. It was actually pointed off, and yet the plane would kind of go in this path, and it looks kind of funny. In fact, they call it crabbing because it looks like a crab that walks sideways down the beach. I don't look strange if you ever see it, but it actually makes sense because as far as the plane is concerned, it's cutting straight through the wind, and the wind is pushing it just right to land where you want to go. So there's a bunch of other interesting mathematics that our instructor Jerry Hauser pointed out, and if we have time, maybe in the future episodes I can show you some more. He packed quite a bit of math, and there's of course some he didn't even mention in there that comes with flying a plane. So if you don't want to learn how to fly planes and you don't like math, I don't want to scare you too much because they have lots of nifty little shortcut devices to help you out. There were several different instances of mathematics that Jerry brought up when he was talking about all the stuff that goes into flying planes, but there was one I thought we could follow up on, and that's where he mentioned, if you point your plane in a certain direction and fly there, you don't always get there if you have wind factored in, and of course normally you do. So I was going to show you a little bit about how that works. In fact, I've drawn a very simple scenario on my math cam here where we're going to fly a plane. I have my plane on there, and we want to fly from A to B. It's due north. We want to fly, and I'm making this up, but I just said let's suppose we have a 30-mile-an-hour wind, and it's pointing a little bit 20 degrees south of east. Well, the problem is if you want to take your plane here and fly it, and you just aim for point B, you're intending to do this, just fly to point B. What's really going to happen is the wind is going to push you, and you're going to end up over here somewhere. So to make up for it, you actually have to aim to the left to compensate. So you kind of aim this way, as if you're going to hit a point maybe over here somewhere, and then when the wind kicks in, you're going to actually compensate for it, and you will end up where you want it to be. The funny thing is, though, as it happens, you will always be aiming off to the left. So as you fly in a straight line straight north, your plane will be kind of aimed diagonally, and it looks kind of funny. I've actually seen it myself from the sky when a plane passed below me. But this really does happen, and just in case you think I'm making this up, I have a cool video to show you. This is from YouTube, and it's a video of testing a Boeing jet on a landing. And by the way, they call this crabbing. It's called crabbing because you kind of go sideways like a crab across the beach. But look at this plane trying to land. You can tell it's not pointed at all in the direction of the runway. It's actually quite extreme. Now, once he touches down, he's going to have to straighten the plane out to, of course, stay on the runway with the tires. But he sure wasn't at first. So this was a test run. Hopefully it's not that extreme, when you're out flying for the holidays. I know a bunch of you are planning for a trip maybe over the holidays to visit family or have a vacation, right? So we thought this would be an appropriate bit of mathematics to show you having to do with having a little flight over the holidays. So anyway, how would you work this out? What direction you should actually fly? Well, I have my made-up scenario here. We're just going to do a little example, and I'll show you how this would work mathematically. So what we want to do, we're going to use these mathematical objects called vectors to do this. You don't have to know too much about them. All you got to understand is these arrows I drew with my plane here. This is called a vector. The length of it's going to represent the speed that we're flying at, and the direction, of course, is what's indicated with the arrow. And so I'm going to actually rewrite my wind vector here, and I'm going to place it up at the top here, and I'll explain why in just a second. So we'll put the wind vector here, and remember this was 30 miles an hour, so the length of that vector should actually be 30 in whatever units you're using. The length of this vector would be the speed that you're actually flying. And remember, we're going to aim a little bit to the left to try and hit that spot, and so we land perfectly at point B. So I'm going to draw the direction that I think we're going to fly our plane here. So here's my ruler. I'll try to make it nice for you. We're going to fly in this direction, and the length of this vector would actually be the speed that my plane really goes. And I'm thinking of a small plane like a Cessna, and the smaller ones of those types of planes go about 100 miles an hour. So let's just say you're flying at 100 miles an hour. So your whole job is to figure out what angle right here to fly at to hopefully hit the spot that you want. So there are some fancy things we could do with vectors. If you've actually, if you've advanced enough to have dealt with vectors in a class, you can talk about their components and how they add and everything. But we're not going to do that. We're just going to use some simple trigonometry and some angles to try and work this out. But the way vectors add, and this really is how speeds combine, is if I draw these accurately, if this is 100 units long and the angle is correct, and this wind vector here is 30 units long and its angle is correct, you simply add them by drawing one after another. Where this one ends, you start the next one, and where that one ends, this blue line is called the resultant, and that will be the direction you will actually fly. And the deal is we want the resultant to be due north. We have to fly a bit to the left to make it happen. So we're just going to use some triangle stuff. I thought we could do is I'll redraw our picture here, and I just want to use triangles and angles. And there's one piece of information I'm going to need, and we'll see if we can figure it out here. So I'll redraw my triangle. So it's something like this. And I'm going to go ahead and label what we know, and then we'll see if we can figure out anything else. This side is 30. I know this is 100. I don't know that north heading side. We might figure that out as we go. I want to know this angle. We don't know it right now. Do we know any other angles? And I'll tell you, we do need to know one more in order to proceed here. But we do, if you look carefully at my picture, actually. If you go back to where this wind vector is, I did tell you that if you look to the east, it's a 20-degree angle to the south that the wind is blowing at. Well, if we draw a little bit of extra information, I can actually figure out some other angles in here. For instance, this little angle in the triangle right here, I'm going to use a fact about triangles. It's true. This is true for any triangle. All the angles always have to add up to 180 degrees. So I have a 90-degree angle in the corner because I drew a nice little right triangle. I have 20 used up here. That's already 110. And that means I have left over 70 for that little corner. That means I can figure out this angle up here, because if you look along this vertical line, that's a half circle or 180 degrees. If I've used up 70 for this part, I must have 110 left over for that inside angle. So that angle there is actually right here. This is 110 degrees. Well, believe it or not, that's enough information for us to go on to figure out this angle down here, which will tell us what direction we want to fly. So what I'm going to use to do this, and you would see this in a trig class. If you haven't had trig for a while, this might be a good little refresher for you. I'm going to use the law of sines. And what the law of sines says is you can make some simple ratios by comparing sides and the sines of angles. So this is always true for any triangle, whether it's a right triangle or not. Ours, of course, is not. The only thing you have to understand about the notation here is that a capital A angle is opposite a little a side. So for example, if I call the angle we want capital A, then 30 opposite it has to be the little a. And if 110 is angle B, well, then the 100 speed here is little b. So let me fill in what we've got here, and that'll be enough information, actually. So we'll have 30 over sine A, and I don't know sine A, we're going to figure it out, equals B was 100, and angle B is 110. So let's say you're in algebra class. How would you solve a little fractional equation like that? Well, the easiest way, of course, is cross-multiplying. So that's what I'm going to do. I'm going to multiply these two, the sine A times 100, and these two, the 30 times sine 110. And those have to be equal. So let me just divide both sides by 100, and we're going to have our answer. So sine A has to be this amount. Now, I did this on a calculator. This turns out to be about 0.2819. The only thing you have left to do, that's your value of sine. You have to reverse that. So you have to use an inverse sine function. So our angle we want, angle A, is actually a reverse sine of 0.2819. I did it out, and it comes out to be about 16.4 degrees. So that's all you'd have to do. You have to aim your plane 16.4 degrees to the left to hit the destination you want if that wind speed stays steady like that. Now, the pilots, if you're going to train to be a pilot, they have some cheater ways out of this. In fact, you saw our instructor, Jerry Hauser, demonstrate some computations on this. He called it a calculator. I have a little one with me here. So it looks like this. And this thing, this is the back end of it. This has some sliders and some rotating circles here. And you can make some marks with indicate your wind and turn the dials just right and figure out where to fly, as a little shortcut. So you don't have to sit down and do algebra equations if you don't want to. But if you do feel yourself interested in flying, I have a little information for you. We have a nice website you can look at for Palomar College. We have our own instructor program, and this is the AOPA website. If you want some any information about learning to fly, that's probably a good source for you. It's one of the main pilot sites. And here's our own Palomar website. If you want to check that out, it's just palomar.edu/aviation, and that's Jerry Hauser's department. He can help you out if you're tempted to learn to fly, or maybe you'll just fly over the holidays for fun. In the meantime, I was going to show you this thing called Benford's Law, and this is not something you would see in most math classes anyway. And to be honest, it's not really a law, it's more of an observation, I guess. But just to give you the idea of this mathematical observation, let's say I had you for 6 months or so keep track of your finances. And I want you to write down everything you spend with cash, any checks you write, if you write checks these days, anything you do online, if you buy anything online, if you do any TM transactions, you use a debit card, credit card, anything, I want you to write it all down for 6 months. I would guess you'd have this huge list of amounts that you've spent. And I said to you, okay, now I want you to take all those numbers and look at them, and look at just the first digit, and tell me how often the first digit's a 1, and how often it's a 2, and how often it's a 3. And you know what? I would probably guess that they'd show up kind of equal. They'd be sort of random, you know? There'd be about the same number of 2s and 3s and 4s, etc. Well, Benford's Law says no. It says that will not happen. In fact, they'll come out very unequal. So I actually have a graph on my computer that Benford's Law shows you what the predicted breakdown would be. Now, this is only for the first digit. And I took this graph from an excellent website that Mathematica has built, some mathematical software. So this first column here in our little bar graph is showing you that you should have about 30% digits 1 starting your numbers. And then from there, there's about half the number of 2s. I think it's about 17%. And then from there, you'd have lower number of 3s, and then 4s, and then 5s, etc. And you'd have the least number of 9s. So first of all, you might think, why would that be true? That seems very odd. Well, I can give you maybe a little bit of explanation if you think about your money, because if you go spend a bunch of money, chances are you're spending more at lower amounts than higher amounts. You know, you're probably doing more charges for $10, $12 than you are for $80 or $90. So maybe you could see some lower charges showing up more than higher ones. But still, you know, you'd have $20, $30 charges. Well, think about once you get to 100. So once you get to $100, if you think about it, you're going to have a starting digit of 1 all the way up until you would hit $200 charges. So for this whole span of $100, they all start with 1 unless you go to much higher amounts. So maybe there's a reason why you might have some, you know, more starting with a 1 than some other numbers. But here's the weird thing. This Benford guy that came up with this observation, he collected tons and tons of sets of numbers, and he collected them from things you would think have nothing to do with each other. Like, he took baseball statistics, he took stuff from the populations of cities, he took areas of countries, he took areas of rivers. He opened up the newspaper and just wrote down every number he saw, no matter where it was, whether it was on, you know, the stock prices or sports statistics or prices of stuff, didn't matter. Any number he saw in the newspaper, he would write it down. And when he compiled all these numbers, he found this exact distribution happening, that the 1 would show up about 30% of the time, the 2s, 3s, and 4s, less and less, etc. In fact, I have another graph I was going to show you, and this one is from some recent data, and I had to expand it so you probably can't read the words very well, but I can tell you what's going on here. Each of the numbers, 1, 2, 3, has 4 bars there. The first bar in dark blue is the Benford's Law prediction, what they think it should be. The second, third, and fourth are different colors. The second one is number from the newspapers. Third one is census data from 1990, so that's, you know, current population data. And the fourth one, the yellowish one, is numbers from the Dow Jones stock average. So again, things you'd think would have nothing to do with each other, and yet they still follow this strange law. And in fact, there's even a mathematical formula that'll tell you how the law works. And I don't know if this will surprise you or not. I'll write the formula down on my math cam. The formula is log 1 plus 1 over d. This is the chance that d will be the first digit in one of these numbers. So, you know, 2 issues. Why is this true? And number 2, why does log have anything to do with it? If you've had some, you know, algebra classes past the beginning ones, you've probably seen logarithms. Well, I can kind of give you a little idea of why this happens in a natural way. If you take sets of numbers like populations, try and think about let's say a small city is growing larger. So let's say a city starts with 10,000 people. So I'm going to say 10,000 people in my city population, and let's say it takes, I don't know, 20 years to double. So in 20 years, I have a population of 20,000. Well, if it's growing exponentially, which is the way most populations grow until they reach kind of a maximum size, that would mean if you waited another 20 years, it wouldn't just add another 10,000, it would actually double again. So lots of populations do this, and also financial things do this, like oftentimes the stock market prices or costs of things. So if I waited another 20 years, what would happen is you'd be at 40,000 now. And if I waited another 20 years, you would be at 80,000. So look at these numbers. In the first 20 years, all your populations start with a 1. You got 20 years of numbers starting with 1s. But the second set of 20 years, same amount of time, is split. Some of those numbers start with a 2, some with a 3. And the third set of 20 years is split even more. You have 4, 5, 6, and 7 as starting digits in the same span of time. So if you were to write down the population every month or every year, you'll see a lot more with 1s than with 2s, 4s, and 8s, because that's how the numbers tend to climb. And it's partly due to our number system that once you reach 10, you carry over to a new decimal place or column, and you start a number starting with 1. Why would logs have anything to do with it? Well, without going too much into logarithms look at the exponent on 10, not the number itself. If you take a log of a number, like this population of 40,000, the number you get is the exponent on 10. So basically what Benford's law says is that if the numbers aren't going to be evenly distributed with the first digit, but the log of them probably is. So that accounts for these powers of 10 we observe. And and some people have actually suggested, you can decide for yourself if this is true, some people actually suggested that our senses are more tuned to logarithmic changes or changes in magnitude and not just little incremental changes. Perfect example, sound. If you look at sound, our ears are more attuned to something getting twice as loud or twice as powerful, not just a little bit more. Anyway, maybe we'll do that at some other show. So what does this do for you? Well, or why do they use this in the real world? They actually use this to catch accounting fraud. So in fact, they caught a guy in New York. He was cooking the books, and what he was doing was he was taking the actual costs or expenditures he was playing with, and he would often take a number that started with 1, because that was kind of a low amount, and he'd change the 1 to a 7 or a 9. That way he could get more money coming into the account. Well, they did Benford's law in his data, and guess what? He didn't have near enough 1s. So they caught him. He was arrested for fraud. So see what I've done for you? I've shown you how to cheat on your accounting and not get caught. No, that is not the message. No, not at all. No, it's just an interesting observation. And of course, it's not always true, but it does tend to be true with numbers like these financial numbers or populations, etc.